Hello, let's get started on density, our second week of our study of matter for our second unit. So density is a property of matter that helps us to do several different things, and we're going to look at those different applications of density today and then applying it throughout the week. So density is, as we said, a property that is related to both mass and volume. So we're going to start by defining mass and volume. And we've talked about both of these before, that mass is a measure of kind of how much stuff is in a sample, or, we've said the matter. Another word for matter is kind of, casually stuff. So the measure of matter in a sample is the mass. And we measure that in grams or kilograms when we are working with mass. And in a particle diagram, each particle represents one unit of mass. So when we're looking at kind of visualizing mass, the more particles there are, or the larger particles there are, that would be more mass. So let's make a note of that. Each particle in a diagram represents a unit of mass. That will be helpful when we're looking at example 1. 1 unit of mass. Okay. And then mass, just a quick note here, is different than weight, because mass is telling us how many atoms are inside of a sample, whereas weight is telling us how much force is being pulled down on that mass. Now, when we're on the earth, mass and weight are going to be related because the amount of mass and the amount of force being pulled down it are related. But if I were to go out into outer space, let's say we go onto the moon, now we have a different force of gravity, so the weight will be less, but the mass of the object will still be the same. Just because I go to the moon and now I put a scale out and it says I weigh, half my weight, that doesn't mean I am actually less stuff. I still am made up of the same atoms, the same grams of stuff. Now I just have a different force pulling on me because of where my location is. So just a quick note there, mass is different from weight because weight depends on gravity and the force being pulled down on it. Mass is just the stuff or the matter in our sample. Okay. Now on to volume. Volume, we've talked about, measures space that an object takes up or that the sample takes up. And it's calculated if we have a cube or even like a block. It's calculated by length times width times height. But sometimes we have kind of weird objects, or we call them irregular objects. Let's say like a rock or a paperclip or a penny, and you want to know its volume. Well, you can measure it by displacement of water. So you'd fill up a graduated cylinder with water to a specific height that you know of. So let's say we fill it to 5 milliliters, then you put the rock in and then the water goes up. Let's say it goes up to 7 milliliters. Well, it was at 5, you added the rock, and it rose to 7. So the difference between the two levels has to be the volume or the space that the rock took up. So you could subtract the two numbers to find the volume of the rock. 7 was our final spot. 5 was where it started. 7 minus 5, that means the rock had to have been 2 milliliters of volume that it's taking up. So we can find volume by length times width times height, which will give us units of centimeters cubed, because we're doing centimeters times centimeters times centimeters, or it can be found by water displacement for irregular shapes. Like we said, a rock, a penny, a paperclip. For irregular objects. And when we measure it this way, then our volume is in milliliters. And just for your information, 1 centimeter and 1 milliliter are exactly the same amount of space. So you can use those interchangeably really well. So note here, 1 centimeter cubed is actually defined as 1 milliliter. So both of them are telling you the same amount of space. Now, the last part of our notes here is where we look at the relationship between mass and volume, the density. So our density is a ratio that is between mass and volume, and it's measured grams per milliliter or grams per centimeter cubed, depending on what your volume measurement had units of, but like we said, they're the same, so it really doesn't matter. You can use either one. A casual way to define density other than that ratio between the two is stuff or mass per area space. If you think about a population density, when you have a high density of people, it's really smushed in together because there are a lot of people per area space. If you have a low population density, now it's a little bit more dispersed. You have less amount of stuff per area space. That would be your density. It represents the compactness of the particles. So when we have things that are really compact and smushed together, that would be highly dense. And if we have particles that are separated from one another, not as compact, that would be something that is less dense. So it is also kind of a one-word definition, compactness, if you will. Okay, so stuff per area space, or the compactness of the particles. And you can calculate density by dividing mass over volume, and it actually sort of looks like a heart, right? M over V, if you ever forget and need to remember. Density equals heart, draw a line, and now you have your equation M over V. Okay, so let's do some applications of density. First, visualizing mass, volume, and density. For each pair, circle whether A or B has a greater mass, volume, and density. In some cases, they may be equal. We just said that mass is each particle. So for A and B, we have much more particles or dots in box B, so that one has a greater mass. Volume is the amount of space that the box takes up. Which one has a bigger space? That would also be B. And then we're going to look A and B. What about their density, or the compactness of their particles? Well, it actually looks like they're the same. They're equal because their mass and volume change at the same ratio. Higher mass had higher volume, lower mass had lower volume, kept the compactness of the particles the same. B has a slightly different density because their mass and volumes don't follow the same ratio. So our particles, or mass, are greater in box B, but our volume is equal. So they're not changing when we have a higher mass. Our volume didn't increase with it, which in turn gives us a higher density of box B. If we had a greater volume and a greater amount of mass, then our density would be able to stay the same. What do you think might have happened if we had the same mass but a smaller volume? Perhaps it would get more dense. Smaller volume, more mass means we're going to have to squish it in tighter. Similar idea here. Well, we're keeping the volume the same. Okay, so that's visualizing mass, volume, density. Next, we have a density column. Density is part of whether the defining factor for if something sinks or floats. Okay, when you have a higher density, things will fall to the bottom because they're so compact. They're really dense is really what makes things sink. And the things that float, their particles are a little more dispersed and they will float on top. Okay, so if you think about it maybe as the heaviness, if you will, when they're more compact, it makes them fall to the bottom, and then when they're not, they float on top. So our most dense would be at the bottom, following this first piece of directions, and our least dense would be on the top. The same is true for any particles, gases. It doesn't have to be liquids. That's just what example we have here. The density of water is 1 gram per milliliter. Syrup is 10 and oil is 1/2 gram per milliliter. Draw where a penny would land in the column if its density is 7.2. Well, 7.2 is greater than oil and water, so it will sink in both of those, but it will float in syrup. So we'll put it right here. There's our penny. A rubber duck floats on the oil. What must be true of its density? Well, if our little ducky floats up here, that looks not like a duck, but bear with me. That duck has to have a density less than that of oil, which would be 0.5 grams per milliliter. We don't really know anything else of the duck's density other than it's less than 0.5 if it's floating. We're going to finish example 3 and example 4 in a part 2 video.